Hello, Algebra 2 people. So today we're going to be taking a look at starting the 5th unit, which involves more of those roller coaster graphs, so more ups and downs than just one little parabola would. And to do that, we're going to start with some vocabulary and some basic polynomial operations, most of which you already know, and a new thing called synthetic substitution. And you should have some guided notes from me as well as a calculator. Those guided notes follow along with this PowerPoint. So first we want to start with what types of polynomials exist out there. So what kinds of things do we consider polynomials? And what is that word? What does that mean? So first thing you should remember from Algebra 1 is that polynomials can sometimes have one term. In this case, it's called a monomial. That's when it's just a number or a variable or the product of a number and one or more variables with whole number exponents. So if I was going to take that description and write an example of that, and you should in your notes, these might be what a monomial looks like. Just 8, just negative 2x, just 3x squared y, just 1/2 x squared. There's one term, okay? Now, two terms are called binomials. So that's when there are two pieces to our puzzle here. So x to the 4th and a subtract 8. X to the 4th is one term, subtracting the 8 there represents the other term. And then we looked at already this year three terms called trinomials. And we used the AC method whenever we had to factor them. So basically, three terms looks like something we're familiar with. And four terms or 5 terms or 6 terms, after that point we stop giving it a special name and we just call it a polynomial. So more than those 3 terms there, he would be a polynomial. More definitions we should remember. Standard form. Standard form is when we rewrite the polynomial, rewrite the problem so that the highest power comes first. So the highest exponents come first, like 3x squared, then 2x, then the constant 8. So we can see that the highest exponents come first, and then exponents go in decreasing order. Okay, so each exponent then decreases in value. The degree is a special word we use to describe the highest exponent in a polynomial. That highest exponent needs to be on the variable. So the degree indicates what's the highest power we see on the variables that are represented in that polynomial. So if I was going to look at 3x squared plus 2x plus 8 again, I would say that the degree is 2, because 2 is the highest exponent represented on a variable there. Okay, so, I forgot I animated those in there. Nice! So underneath that, you see a chart in your notes about degree and what type it represents. The first example in your chart is negative 14. Oops, I have a 14 here. So for negative 14, that's an example of a constant. Because there are no exponents on variables there, he has a degree of 0 because there's no exponents. The 5x minus 7, the highest degree we see there would be a 1. The highest power that's on that expression there, on that variable, is a 1. So he is a first degree. Most of the time, or all the time, this thing will graph into a line, so we call him linear. And when it's an x squared, the highest power is a 2, so the degree is 2, and we call him quadratic. And it can continue. If you have x to the 3rds, that's a cubic because the highest degree is 3. And an x to the 4th problem, like this, he is a quartic because his degree is 4. So you see that table there in your notes kind of illustrates the same idea. So if we keep going, we're going to take a look at what's called function notation, just to kind of make a comparison here. You don't have this part in your notes, but just take a look. This is what we're normally used to. This is called an expression. It has no equal sign, but we can simplify it, factor it, but we cannot solve it. When we put an equal sign there, now we can graph it. This is an equation. We can graph, we can solve. And sometimes now, from now on actually, you're going to see that y turn into the f of x notation again. Remember, it's like a y, but it represents that we're talking about a function. So the letter names the equation. We're not going to see that y appear quite as much as we would before. So you have a couple examples in your notes on deciding if things are a polynomial. If so, write it in standard form, state the degree, what type, and leading coefficient. So this first example, let's take a look at him. Is this a polynomial? The answer is yes. This is a polynomial because when I look at him, all of the exponents here are whole numbers, 2, 4. That's a whole number exponent, so we can go ahead and classify that as a polynomial. Now, how do we write it in standard form? We need to rearrange the terms here so that the x to the fourth, because that's the thing that has the highest power, comes first. So I would rewrite this as h of x, that's his name, the h function, if you will. And he needs to be written so the x to the fourth comes first. Then after that, the next term that has the highest power would be the x squared term. So it would be negative 1/4 x squared. And then after that, we just have a 3 left, and he would go at the end. So that's written in standard form. What degree does this thing have? The degree would be 4, because the highest power is 4. State the type. Because the degree is 4, if you look back in that chart you have, we're going to call this a quartic equation or a quartic function because the highest degree is 4. And quartic represents the 4. What's the leading coefficient? The leading coefficient is that number that's in front when it's written in standard form. So what's in front of the x to the fourth? That would be a 1, so the leading coefficient is a 1. Let's take a look at that next example. Is this a polynomial? Well, at first glance, you might go, hey, there's a whole lot of terms there. That's a polynomial. But when I look at this, I'm not so sure. This guy has a 3 exponent, but a negative 2 exponent is present. Negative 2 is not a whole number. Whole numbers are 0, 1, 2, 3, 4, 5, 6, positives and 0. That is negative. That is not a whole number. This is not a polynomial at all. So we can't write it in standard form. We can't state the degree. We can't identify that leading coefficient there. Okay, so what are some things that we commonly do with polynomials then? After we have these big long problems where there's lots of pieces, what can we do with them? Most of the time we substitute x values into them, and there's a couple ways to do this. We've been plugging in using our calculator into these things for a long time. And one of the ways that you're most familiar with is through direct substitution. Now, there's more than one type here of substitution. In fact, there are 2 types of substitution, one of which you're familiar with and one that's going to be new to you. Substitution that you know is direct substitution. That's the way we've been using and learning since Algebra 1. Plug that number in, chug it out, use order of operations, use a calculator, whatever you got to do. And then there's this new type of substitution, this guy right here. Synthetic substitution is going to be new for us. It's another way to substitute that gets us that same end value, but it looks completely different than anything you're used to. So if we remember direct substitution, this is the example you have in your notes. Let's evaluate this guy. Let's figure out when x equals 3, what this polynomial works out to make in terms of his value. So I'm going to say the function with 3 plugged in it looks like this. 2, 3 to the 4th minus 5, 3 to the 3rd minus 4, 3 plus 8. And there's a whole lot going on here. If I was going to evaluate this old school with a little bit of calculator help, I would have to do order of operations, which means that I first do anything that has an exponent. So 3 to the 4th turns into 81. So this is like 2 times 81 minus 5. 3 to the 3rd is 27. Minus 4, 3, plus 8. Those are the only exponents I have there. Now I have to, in order to do order of operations with PEMDAS, parentheses must need to be done, exponents next, then any multiplying. So 2 times 81 would be next. That's 162. This guy times this one, 5 times 27, oh my, 135. This is a minus 12, this is a plus 8, and now we do any adding and subtracting. So again, going to your calculator, minus 12 plus 8, I'm typing away here, and 23 is my final value. So the function with 3 plugged in it equals 23. You've been plugging in numbers for a long time. You had to do it to graph parabolas. But the new way to plug in numbers is called synthetic substitution, and it's actually really, really cool. And it only involves fewer operations and calculations than direct substitution. In fact, I would completely challenge any single one of you to try to direct substitute quicker than I can synthetic substitute. It's really quite fast, especially if you just kind of know the process and understand what's going on. But it starts with a different setup, and that's what's kind of different for people. So it's set up differently. See that same problem? We have a 2x to the fourth minus 5x to the third minus 4x plus 8, and we're going to evaluate when x equals 3. Essentially what happens is we take these terms and we put them in order. X to the fourth, x to the third, then there should be an x squared, then an x, then a no x or plain number. And if I'm going to plug in 3, that means I'm going to place a 3 on the outside of this sort of upside down L sort of box, long division sign, however you want to describe it. And then I just take the numbers that are in this problem. So if it's a 2x to the fourth, I'm going to write that first. Then comes a negative 5x to the third. After x to the thirds, there should be x squareds, but I don't have any in my problem. Then there should be x's. Well, I have negative 4 of those. And then there should be plain numbers. I have 8. So now to do direct or synthetic substitution to get the same answer as we did before, we're going to drop down that 2. Drop it like it's hot, okay? Take that 2 outside the box. Then we take the 3 times the 2 and we multiply them. That makes 6, and I'm going to line them up underneath the next guy. And then I just add those together. Negative 5 plus 6 is a 1. Then I 3 times 1 again. 3, line them up underneath the next number, add. Then 3 times 3 again, that's 9, line them up, add. 3 times 5 is 15, line them up, add 23. Isn't that what we got when we did that direct substitution? But it took us quite a bit longer, and we had to have a calculator, and it was a little bit messier. So the function value when 3 is plugged in is still 23, but we did it this synthetic substitution way, which is so cool. Okay, here's another example. Don't write this in your notes. Just watch and see if you can see where I'm setting this thing up and how this works again. So watch the process. So first thing I'm going to do is draw the upside down little box deal. And on the outside, I'm going to place that 2 because that's what I'm plugging in. Then I'm going to take the coefficients, the numbers that are in front of the variables here, and place them in a row here across basically the top of the box. So first I start with a negative 3x to the third. After x to the third should come x squareds. I do have an x squared. There's only one of them. After the x squared should come an x. I do have an x. There's negative 12 of them. After the x should come the plain number, negative 5. So everything's set up, and now we can do quick synthetic substitution. We're going to drop it like it's hot here. The first one, drop him out, negative 3. And we multiply. So here we multiply on the diagonal. 2 times negative 3 is negative 6. And now we add, negative 5. Now we multiply. 2 times negative 5 is negative 10. Now we add, negative 22. Now we multiply. 2 times negative 22, negative 44. Now we add, negative 49. Done. This tells me that the value of that function, when I plug 2 into it, would equal negative 49. And I could test that out if I wanted to do old school and go negative 3 times 2 to the third minus 2 squared minus 12. I could do all this times 2 minus 5, and you're going to get that same value, that same answer. But synthetic substitution is quite a bit faster, especially when all those terms become kind of long there. So let's do one more. This one is in your notes. Make sure you write this one down. Evaluate when x equals negative 1. So again, we're going to draw the upside down box. Stick negative 1 on the outside. And looks like we're starting with a negative 2 x to the fourth. After x to the fourth should come x to the third. We have negative 1 of those. After x to the third should come x squared. Whoa, we're missing the x squared in there. He's missing. So we're going to put a 0 as a placeholder. That 0 is very important. That tells the problem or the process here that we don't have an x squared. We need to mark that spot. Otherwise, we stop our process too early. So we're missing an x squared, but we do have an x after that, and then after that would come the plain number, which we have. So it's all set up. Now we drop it out. -2, multiply. -1 times -2 is +2. Add 1. -1 times 1 is -1. Add -1. Multiply 1. Add 5. Multiply -5. Add -10. Woohoo! Okay. Final answer. If I were to take this g equation or this g function and plug in -1, my final answer would be -10 when I calculate that all out. Quite a bit easier, not as messy, not as many powers. You don't have to worry about parentheses. It's just all adding and multiplying. That's why synthetic substitution is so cool. So be sure that you're aware that there are these new ways to substitute, and we're going to get some more practice on this tomorrow on an assignment that we're going to get in class. Okay? Thank you very much for watching.